The original 15 amp circuit was insufficient for the load, as the tanning bed alone was drawing 11 to 12 amps. With all devices in the circuit operating simultaneously, the total load reached 13 amps, exceeding the circuit's capacity. Upgrading to a 20 amp breaker was appropriate to provide adequate current capacity. Heat can reduce the current carrying capacity of electrical components, including circuit breakers. While the location of the panel in direct sunlight could contribute to temperature rise, it's unlikely to be significant enough to affect the operation of a properly sized breaker, for example, 20 amps rated for number 12 American wire gauge wire. It's important to note that the 13 amp load measurement does not account for potential surge currents when the tanning bed is turned on or off. These surges can briefly exceed the steady state current draw. The presence of bathroom lights, doorway lighting, and an office in the same circuit may be a concern if these devices are used heavily, for example, during peak hours. It may be advisable to consider separating the tanning bed onto a dedicated circuit to isolate it from other loads and avoid potential tripping issues. Upgrading the circuit to 20 amps was a reasonable solution to address the immediate problem of circuit tripping. However, it's important to monitor the circuit and observe its performance over time, especially considering the potential impact of ambient temperature and surge currents. If there are any concerns or persistent issues, further diagnostics and evaluation may be necessary. When addressing a circuit overload situation, it's crucial to follow a systematic approach that considers all relevant factors from load calculations to environmental conditions. The first step is to accurately determine the existing load on the circuit. This involves identifying all devices connected to the circuit and determining their individual current draw. Appliance nameplates typically list the current draw in amps or the power consumption in watts. If the power consumption is given in watts, you can calculate the current draw using the formula amps equals watts divided by volts. Remember to use the correct voltage for your system, which is typically 120 volts in residential settings. Once you have determined the current draw of each device, add them up to find the total load on the circuit. This total load should not exceed 80% of the circuit breaker's rating to prevent nuisance tripping. For example, a 15 amp circuit should not carry more than 12 amps of continuous load, and a 20 amp circuit should not carry more than 16 amps of continuous load. In the case of the tanning bed, the fact that it was drawing 11 to 12 amps by itself indicated that the original 15 amp circuit was already operating close to its maximum capacity. Adding the additional load of the bathroom lights, doorway lighting, and office equipment pushed the circuit beyond its limit, causing the breaker to trip. Upgrading to a 20 amp breaker was a reasonable solution because it increased the circuit's capacity to 16 amps of continuous load, providing a buffer for the existing load and potential surge currents. However, it's essential to ensure that the wiring is also appropriately sized for the new breaker. In this case, the fact that the wiring was number 12 American wire gauge meant that it was rated for 20 amps, making the upgrade safe and code compliant. If the wiring had been smaller, such as number 14 American wire gauge, it would have been necessary to replace it with number 12 American wire gauge or larger to prevent overheating and potential fire hazards. Ambient temperature can also play a significant role in the performance of circuit breakers. Circuit breakers are designed to operate within a specific temperature range, and their current carrying capacity can decrease as the temperature increases. This is because the internal resistance of the breaker increases with temperature, leading to greater heat generation and a reduction in the amount of current it can safely handle. The location of the electrical panel in direct sunlight can contribute to temperature rise, especially during hot summer months. While it's unlikely to be a major factor in this case, it's still something to consider, particularly if the panel is located in an area with poor ventilation. To mitigate the effects of ambient temperature, you can try to shade the panel from direct sunlight or improve ventilation around it. You can also consider using circuit breakers that are specifically designed for high-temperature environments. Surge currents are another important consideration when dealing with electrical loads that cycle on and off, such as tanning beds. Surge currents are brief spikes in current that occur when a device is first turned on. These surges can be several times higher than the device's steady-state current draw, and they can trip circuit breakers if they exceed the breaker's instantaneous trip rating. To address surge current issues, you can use circuit breakers that are specifically designed to handle them. These breakers, often referred to as 8-tracker or motor-rated breakers, have a higher instantaneous trip rating than standard breakers, allowing them to withstand brief surges without tripping. You can also use surge suppressors to protect sensitive electronic equipment from damage caused by surge currents. Another important consideration is the potential impact of other loads on the same circuit. In this case, the presence of bathroom lights, doorway lighting, and office equipment on the same circuit as the tanning bed could contribute to tripping issues, especially if these devices are used heavily during peak hours. To avoid overloading the circuit, it may be advisable to separate the tanning bed onto a dedicated circuit. This will isolate the tanning bed from other loads and ensure that it has sufficient capacity to operate without tripping the breaker. When installing a dedicated circuit, it's important to follow all applicable electrical codes and safety regulations. This includes using the appropriate wire size, circuit breaker rating, and grounding methods. It's also important to properly label the circuit breaker so that it can be easily identified in the future. In summary, troubleshooting a circuit breaker tripping issue requires a systematic approach that considers all relevant factors, including load calculations, ambient temperature, surge currents, and the potential impact of other loads on the same circuit. Upgrading to a larger breaker may be a reasonable solution in some cases, but it's essential to ensure that the wiring is also appropriately sized and that all applicable electrical codes and safety regulations are followed. In this specific case, upgrading to a 20-amp breaker was likely an appropriate solution, but it's important to monitor the circuit and observe its performance over time to ensure that it's operating safely and reliably. If there are any concerns or persistent issues, further diagnostics and evaluation may be necessary. Additional things to consider are as follows. Firstly, check the condition of the existing wiring. Look for any signs of damage, such as cracks, breaks, or corrosion. If the wiring is old or damaged, it may need to be replaced. Secondly, inspect the circuit breaker panel for any signs of corrosion or overheating. Make sure that all of the connections are tight and that there are no loose wires. Thirdly, use a clamp-on ammeter to measure the actual current draw of the tanning bed and other devices on the circuit. This will give you a more accurate picture of the loads on the circuit. Fourthly, consider using a surge protector to protect the tanning bed and other electronic equipment from damage caused by power surges. Fifthly, if you're not comfortable working with electricity, it's best to call a qualified electrician to perform the work. The electricity can be dangerous, and it's important to take all necessary safety precautions. Sixthly, always turn off the power to the circuit before working on it. You can do this by turning off the circuit breaker at the panel. Seventhly, use insulated tools when working with electricity. This will help to protect you from electric shock. Eighthly, never work on electrical equipment when you're wet or standing in water. This can increase your risk of electric shock. Ninthly, if you're not sure how to do something, ask for help. There are many resources available online and in libraries that can provide you with information about electrical safety. Tenthly, follow all applicable electrical codes and safety regulations. These codes are designed to protect people and property from electrical hazards. Additional in-depth details to keep in mind includes ampacity correction. The ampacity of a conductor is the maximum amount of current it can carry continuously without exceeding its temperature rating. The National Electrical Code, or NEC, provides tables that list the ampacity of various conductors based on their size, insulation type, and installation conditions. However, these ampacity values are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductor must be derated to account for the increased heat. The NEC provides correction factors that can be used to derate the ampacity of conductors based on the ambient temperature. For example, if the ambient temperature is 40 degrees Celsius or 104 degrees Fahrenheit, the ampacity of a number 12 American wire gauge conductor with THHN insulation must be derated by a factor of 0.88. This means that the conductor can only carry 88% of its rated ampacity. In this case, the rated ampacity of a number 12 American wire gauge conductor with THHN insulation is 20 amps, so the derated ampacity would be 17.6 amps. It's important to note that the ampacity correction factors are cumulative. This means that if there are multiple factors that affect the ampacity of a conductor, such as ambient temperature and the number of conductors in a raceway, the correction factors must be multiplied together to determine the overall derating factor. Voltage drop is another important consideration when designing electrical circuits. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause appliances to operate inefficiently or not at all. The NEC recommends that the voltage drop in a branch circuit should not exceed 3%. This means that if the voltage at the source is 120 volts, the voltage at the load should not be less than 116.4 volts. To calculate the voltage drop in a circuit, you can use the following formula: voltage drop equals 2 times K times I times D divided by circular mils, where K is the constant for the conductor material, I is the current in amps, D is the one-way distance of the circuit in feet, and circular mils is the cross-sectional area of the conductor in circular mils. The constant K for copper is 12.9 and the constant K for aluminum is 21.2. The circular mils of a conductor can be found in the NEC. For example, the circular mils of a number 12 American wire gauge conductor is 6,530. To reduce voltage drop, you can increase the size of the conductor or shorten the length of the circuit. You can also use a voltage booster to increase the voltage at the load. Grounding is an essential safety feature in electrical systems. Grounding provides a low resistance path for fault current to flow back to the source, which helps to trip the circuit breaker and prevent electrical shock. The NEC requires that all electrical equipment be properly grounded. There are two main types of grounding: equipment grounding and system grounding. Equipment grounding connects the non-current carrying metal parts of electrical equipment to ground. This includes the metal enclosures of appliances, electrical panels, and conduit. System grounding connects the neutral conductor of the electrical system to ground. This helps to stabilize the voltage and provide a path for fault current to flow back to the source. The grounding electrode system is the means by which the electrical system is connected to the earth. The grounding electrode system typically consists of a ground rod, a ground plate, or a metal water pipe. The NEC specifies the requirements for grounding electrode systems. Arc fault circuit interrupters, or FSIs, are a type of circuit breaker that is designed to protect against arc faults. Arc faults are dangerous electrical conditions that can cause fires. They occur when current flows through an unintended path, such as a loose connection or damaged insulation. FSIs work by detecting the unique characteristics of arc faults and tripping the circuit breaker to interrupt the flow of current. The NEC requires FSIs in many areas of the home, including bedrooms, living rooms, and dining rooms. Ground fault circuit interrupters, or GFCIs, are a type of circuit breaker that is designed to protect against ground faults. Ground faults occur when current flows through an unintended path to ground, such as when someone touches a live wire while standing in water. GFCIs work by detecting the imbalance in current between the hot and neutral conductors and tripping the circuit breaker to interrupt the flow of current. The NEC requires GFCIs in many areas where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor areas. The electrical codes are a set of rules and regulations that govern the design, installation, and maintenance of electrical systems. The most widely used electrical code in the United States is the NEC, which is published by the National Fire Protection Association, or NFPA. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. It's important to follow all applicable electrical codes when working with electricity to ensure the safety of people and property. Permits and inspections are often required for electrical work. Electrical permits are typically required for new installations, alterations, and repairs to electrical systems. The purpose of an electrical permit is to ensure that the work is performed in accordance with applicable electrical codes. Electrical inspections are typically conducted by local building officials to verify that the work has been performed in accordance with the electrical permit and the applicable electrical codes. It's important to obtain all necessary permits and inspections before starting any electrical work. Safety is the most important consideration when working with electricity. Always follow all safety precautions and wear appropriate personal protective equipment, such as safety glasses and gloves. If you're not comfortable working with electricity, it's best to call a qualified electrician to perform the work.